like me, she's a trained teacher, and she suggested that students' attention span in minutes is equal to their lifetime in years. So I should be finishing promptly after, slightly after 10 to 12. Of course, when I tell you that she teaches children between the ages of 5 and 11, you'll know that I've done what no self-respecting experimentalist should do, and that's to do a large extrapolation. So I want to, partly for fun, but also I think it's partly interesting that you can see how, as a community, we've sort of evolved over the years. There's a villain in this story called Major Colby, and I'll probably end up being quite rude about him, but that's all right, because he worked at Imperial College in the 1930s, so we'll see how things pan out. And unbelievably, the syntax, the definitions are almost seamlessly related to Beverly's talk and also Philip's talk from yesterday. In other words, for whatever reason, you all seem to have chosen the same variables to describe the same quantities. So there shouldn't be too much confusion. There are one or two typos in this, which are some of them deliberate, of course, others aren't, which I'll endeavour to point out as we go through. I'm going to basically pin the description of roughness on boundary layers really all around the log law, and for good reasons we believe there to be a log law on a rough wall boundary layer, and so that's in a sense a cornerstone of permanent boundary layers. You may have a problem if you're a theoretician, you may have a problem with that asymptotic mathematics and the way in which the log law is derived, and you could equally, depending on your initial assumptions, end up with a power law. But I think the log law is probably the best building block that we have, certainly from practical or empirical point of view. And I'm going to spend quite a lot of time looking at pipes, not necessarily just because I like the boundary conditions that pipes give us, but also partly because that's actually really where an examination of the effects of roughness, that's where it all really began in the 1930s. And so that will bring us almost inexorably to the Newton chart, a professor at Princeton who worked with the infamous Major Colby. And all of that is actually based around ideas of self-similarity, and I'll try and explain exactly what I mean by that, because that's actually really quite a tighter constraint than something else which I'm going to spend quite a lot of time talking about, and that is the Townsend outer similarity. And much of what I'm going to say is actually inspired by X and Lumley. Good read. But one of the books that hasn't really been publicised yet is The Structure of Turbulent Shear Flow by Alan Townsend. And he wrote the first edition in 1956, and a lot of people thought, what is he talking about? And then the second version came out in 1976. We were still quite wondering what he actually meant. And you can read between the lines by looking at the 76 edition, and then working out what he left out from the 56 edition. That sort of gives you an idea of his direction of travel in his thought. But he's actually the mainstay of this idea of outer similarity. In other words, the turbulence is uniquely described by outer scales. In our case, it could be the wall friction velocity, and some outer length scale, which could be the pipe radius or channel thickness. And I'll say quite a lot about this because his ideas are actually surprisingly robust. And what I really want to do and this we'll come on to this afternoon, spend some time looking at the effects of very large roughness on self-similarity. And I'll show you some work that we've just finished, where it turns out that with very large roughness, one type of roughness, we appear to get self-similarity with the mean velocity profile, in other words, with the log law. But on another form of roughness, it has the properties where we do not think that we get self-similarity. But it turns out that in both cases, Townsend was absolutely right about outer similarity. And so this is a way of sort of probing the limits of these ideas. So that's really what it's about. It's actually inspired by 10x and Lumley ideas, where you've got on simple flows like this, you've got imposed scales. You've got the wall friction velocity and imposed velocity scale, and you've got imposed length scales. It could be the viscous length scale of the wall, or it could be the outer scale, like the height radius or the channel height. And those are actually very, very powerful ideas, because they are underpinning this idea of self-similarity. And then with a bit of luck, later on this afternoon, we'll see, we'll have some sort of status check and see where we are and work out what would actually be a good way to go. So I'm largely for fun, I put up various types of roughness. Here we've got a turbine blade pitted by the effects of particles, or in the case of steam, by droplets. This isn't Mars, it's actually some sort of surface in Canada. Barnacles on boats, well, I put this in simply because surprisingly one often thinks about CO2 emissions from the aviation sector. It actually turns out that shipping is actually contributing somewhat more. Obviously, fouling of ships' hulls is actually really quite important. Some of you are interested in canopies, so here's a tree canopy. Some of you are interested in meteorological roughness. Well, this is a repeatable roughness, and then we've got some sort of expressiveness there, which is something rather large. And then, if you really want to get serious, you can go to the surface of Mars. I'm not quite sure what the atmosphere is there, but clearly it is a rough surface. To say something about self-similarity, I'm going to build on the lecture that Philip gave yesterday about the log law profile. And in particular, one way of measuring roughness effects is to look at the weight function of the log law, and that's the bit which is not defined by logarithmic variation of the velocity. And Don Coles added on his so-called weight profile. And it turns out that is actually a measure to which the outer layer of the boundary layer is affected by details of the roughness of the surface. And in particular, we'll spend some time looking at Francis Harmer's roughness function, and that says quite a lot about how boundary layers, in other words, they've got a free surface above them, potential fluid, how they behave in comparison to an internal flow. These are actually really quite different. And to do the job properly, we need to think about when the surface becomes hydraulically smooth, and also we'll look at these terms, transitional and full roughness. By transitional roughness, this is something, it's a term that you inherit. It has nothing to do with transition. It simply means that the roughness is of a sufficient size to cause an effect on the flow, but the effect on the flow is not what we would describe as being fully developed. And fully developed roughness is when we get to full roughness. In other words, the effects of roughness on the fluid above it sort of saturate, and this is sort of a quality of asymptotic invariance, which of course determines problems. If you've got any obviously, a lot of this is directly related to what Frederick was just a few quick definitions. Because we're starting off with internal flows, then we actually, and everything is incompressible, so the volume average is just the same as the mass average. U-tool is our friction velocity. Remember, it's a measure of the velocity change of the surface. It has nothing to do with velocity per se, other than the fact that it has units of velocity. We can define a friction factor. This is what Lewis Moody actually used. Other people use a coefficient of resistance, lambda. I will strictly conform to these definitions of lambda as they are defined here mathematically. But it may be that I sort of, for whatever reason, call lambda here a friction factor or something like that. But when you go through the old literature, it's clear that there's a variation in terminology which doesn't really matter. What does matter is that you actually get these equations sorted out. And because we want to do a comparison with external flows, then we also be defining this in friction coefficients. And something which I will allow myself, and I will simply swap as it seems appropriate between delta of boundary layer thickness and a channel height or a height radius. And I can do that because the essence of self-similarity is really that you have an inner length scale and an outer length scale. And then you do the asymptotic matching and assume that those two scale effects are not controlling the dynamics of the range in which you get simultaneous overlap. So, in a sense, the exact definition of the outer scale doesn't really matter. So, I shall use these terms interchangeably. One note on this wonderful variable U-tool, friction velocity. Again, usage in literature varies. Some people working in boundary layers might assume that a velocity scale for the problem would also be the free-stream velocity. I would suggest that that's not a good idea. It's actually really quite complicated, and if you want to follow up on that, there's one of the papers that accompanies these notes which explains that. So really, the only velocity scale we have is U-tool. We have a wall length scale, which in the smooth case will be the friction velocity, well, the kinematic velocity, viscosity divided by the wall friction velocity, and the outer scale will be one of these. Now, so the question is really how do the dynamics change when we actually put another length scale into the problem, that is the roughness height. Okay. Okay. Let me just explain something. Yes, that's a good point. The boundary layer is obviously developing with X. One of the great things about internal flows, channel flows, or height flows, is that provided the development length is long enough, then they're fully developed. In other words, quantities do not change in the X direction. So yes, that's perfectly right, but this quantity, for example, is changing the X in case of the boundary layer, not in and for that reason, when the flow is fully developed, you get very simple relationships with the momentum equation between wall friction velocity and pressure gradient. And that's actually a very good reason for doing experiments in channels or pipes. Quite simply, that you always know what the wall friction velocity is. Actually, I think my last slide simply says that in the case of boundary layers, we need more measurements rough wall boundary layers, where tall wall is actually measured completely independently of the velocity field, and originally you track balance as so I can put these definitions together, and I'll probably swap between lambda here and friction factor F. I think skin friction coefficient does make inference, but they're obviously all simply related, and that's why I put this in the box. If you need to refer back to quite what a variable is, that's the purpose of that box. So, this is a key slide, and probably at the beginning of the lecture this afternoon, I'll recap. This is one of the recap slides. So let's go right back to first principles, dimensional analysis, and if we had a smooth wall, then we wouldn't be worried about the roughness height, and the geometrical properties of the surface would be irrelevant. Philip showed us yesterday that if we follow through the logic of this, then we can have a velocity profile which is a function of y plus and h plus, and the simultaneous overlap gives us the log law. In other words, we have what I would call complete similarity. So here's the question. Let's assume that we've now got a rough surface, and this then becomes complicated. And let's, for the sake of argument, assume that we're looking at distances within about 10 roughness heights. And I take 10 simply because it's one order of magnitude. And then we think about some element on the surface which has a roughness height k. So dimensionally it has an area k squared. So therefore the pressure drop across that roughness element goes as k squared. And let's suppose then that we have behind it a small roughness element. And it's clear that actually the pressure drop across the big element is such that the fluid doesn't actually really see the small roughness element behind it. And I'll refer to that as shielding. That actually comes out of some of the literature from Colebrook in the two things that we can get from this. One is that the wall shear stress variation in velocity quadratically goes as k squared, and that should become apparent in some of the formulations that we come across. What I'm also going to suggest is that defining or understanding the effect of the geometry of the surface on the fluid is actually very difficult. So I might offer one or two ideas that are actually terribly good ideas about what we do about this quantity here. But for the sake of argument, just the problem forward, what we're simply going to do is to take k here to be the maximum roughness height in our distribution, quite simply because it's the element that gives the largest effect. It's the big elements that exert a disproportionately large effect, mostly because the effect goes as k squared. So this is a physical description. Philip showed you yesterday some of the results that came from our spaceman Robinson and his analysis of Stallart's database. And in this case, we can give a plausible explanation about how momentum flux is generated from the boundary layer. It has something to do with these structures. And the information here about the production of turbulent kinetic energy then gets really quite complicated if you then, in this picture, you put some idea about what a specific roughness element is doing. Because at some Reynolds numbers, you may well get a standing vortex pair behind your roughness element. a slightly higher Reynolds number, you might get some sort of type of shedding. You know, I use that term loosely because shedding is usually something that we understand from the problem of an isolated body in a fluid. So it turns out that actually what happens is that the roughness gives us an increase in dissipation rate, but it doesn't actually add anything in terms of an increase in production. And that's basically the essential dynamics, the difference between the dynamics of the viscous sublayer on the smooth wall and something which we have now termed the roughness sublayer. In other words, in our roughness sublayer now we have, basically in comparison to the smooth case, we have an increase in dissipation that's not matched by an increase in production. So from that you can infer that in terms of the overall energy balance there is a mismatch, and that mismatch is really going to be fed by the way in which energy is transmitted back down towards the wall. So from that really quite complicated thought experiment, you can begin to see that actually, as we are suggesting, that actually the effects of the roughness are likely to extend well beyond the roughness sublayer, in other words, well beyond practically about 10 roughness points in the wall. I'll mention rivulets only in passing. You remember one of the first slides I put up, which is a picture of a shaft, which has sort of inspired a lot of people to look at the drag-reducing properties of rivulets. Just obviously the wetted surface area has gone up, so the actual area in contact with the fluid has gone up, so you would expect the friction or the drag to have gone up. But it turns out, in this case, the drag goes down under the right conditions. If you have, if you plot out the drag coefficient as a function of H plus or S plus, where this is our roughness height, H. So remember, plus our wall unit, so H plus is just H cubed or over nu. Or I could equally talk about the spacing. And the drag actually goes down up until you get to about 15 or 20 wall units, and then the drag goes right up. And these sorts of rough surfaces are actually being implemented on Airbus aircraft. And they actually worked. It just turned out that maintaining a surface for this sort of accuracy is actually really not going to, well, it's a real challenge. There are real restrictions about maintaining a surface with this sort of integrity on aircraft. So this is a sort of a special form of roughness, if you like, but having mentioned it, I'll say that I'm just going to so that's one part of the physical description, and the other part of the physical description talks about inner-outer interaction, and I've included in your notes another paper which specifically addresses this. And so it's really a question of the extent to which all roughness can actually affect the rest of the layer. And one of the things that Philip mentioned yesterday was the idea that in the energy balance there's a nice region close to the wall outside the viscous sublayer on a smooth surface, but within the about 15% of the boundary layer thickness, there's this region where we can assume that the flow is roughly in local equilibrium. We call this the local equilibrium approximation. It is only ever an approximation. It's actually quite a useful one, certainly quite robust too. And we simply say that production equals dissipation in terms of kinetic energy. And remember what I've just said about roughness actually inducing increase between these two quantities that can actually only be met by an increase in transport of energy down towards the surface. Then it's clear that if the roughness is sufficiently large, it's actually going to break this approximation because this no longer holds and there's an additional transport term that has to be included in the energy balance. And I call this a bottom-up interaction. In other words, an interaction becomes significant when this local equilibrium approximation is broken. And this arises quite simply because as I let the Reynolds number R plus go to infinity, then K plus, that will also get very large. And what actually determines the interaction then is this relative roughness, the fraction of the outer length scale, here I called it R, height radius, that the roughness height actually occupies. In other words, you would expect this bottom-up interaction to get very significant as K upon R approaches 1. Obviously, if it did approach 1, then clearly we don't really have a boundary there that is can actually be described as such. So we're really talking about ratios of K upon R being something like 10%. And one of the roughnesses that we'll look at this afternoon, K upon R, gets to about 80%. And remember, this is actually based on the maximum roughness height for the reasons just if you've got a bottom-up interaction, then it supposes that you might well also have a top-down interaction. And this is really what this video is attempting to show. And in this case, again, talking about the asymptotic requirement of the Reynolds number going to a very large value. So here we're actually looking at the atmospheric surface layer. This is actually a reservoir in the north of England, and normally it's actually pretty flat, so there are no roughness effects. But it's clear that what you've actually got are large eddies coming down towards the surface. So that's what one might call a top-down influence. And I could write R plus as simply Y plus over Y upon R. And clearly, I can get R plus going to infinity either by letting Y plus go to infinity or by letting Y upon R go to 0. And if I'm simply saying Y plus goes to infinity, I'm simply saying that the bottom-up influence on a smooth surface is actually really quite significant. In other words, I'm sort of replicating the ideas of K upon R going to something which is large. Alternatively, I could suppose that very close to the surface, Y upon R is going to 0, in which case the effects of this interaction are going to become very large, simply as R plus is very large. So those are two complementary ideas, and that's a slight digression, and laid out in that these are the roughnesses that we're actually going to be looking at later on this afternoon. One is simply a large gauge rough sampling. More about that later. This is the fun bit of roughness. I've called it 2.5-dimensional roughness. I'll mention briefly something called 2D roughness. What I'm actually going to talk about are K-type roughnesses, where largely the roughness is 3-dimensional and it's pretty isotropic. In other words, if the flow is going that way or that way, it doesn't actually change the response to it. Clearly, this roughness is really quite anisotropic, and it turns out that the details of these diamond patterns are actually really quite important. In other words, if the flow is going this way, one wouldn't expect the fluid response to be very similar to what it would be going that way. And obviously, what we need is also a benchmark show you these pictures that come from a laser profilometer later on this afternoon. And let's get moving. One of the things, of course, that you can identify that roughness is that if the PDF is Gaussian, then makes things really quite easy. This is the grid roughness, and you can actually see it's not Gaussian. It's got this very large positive skewness on it. Remember, if it's Gaussian, the skewness is 0, the flatness is 3. So the skewness here is large and positive. I've almost called this a pathological type roughness, partly because it sounds good, partly because it's actually very difficult to look. Right, okay. Similarity. This is another key slide, which I'll put up again after lunch. And this is obviously what we have to do dimensional analysis before we start talking about simultaneous overlap, as Philip went through yesterday. And so here we've got all friction, velocity, density, viscosity, y, distance from wall, roughness, height, and the roughness properties. And this is the inner scale description of the mean velocity. And in deficit form, and again, that is important. I'm not going to go into frame invariance here. It's in one of the papers that I've given you. In deficit form, in other words, the decrease in velocity from the centerline value normalized by Newton is a function of distance from the wall, U2 upon UCL, and beta, which is Rotter's, well, maybe trousers actually, the pressure gradient parameter. So delta star is the displacement thickness over the wall shear stress times E by dx. And what goes for the mean velocity should also go for the shear stress. In other words, I can keep the independent variables the same, but then presume that the shear stress behaves in a very similar way. And there is a key difference here between the inner and the outer description. And that is that I have assumed that for the outer layer description, I don't need to know what the roughness is doing. I don't need K, and I don't need roughness properties. And that's really the key statement about inner and outer layer similarity. I'm assuming, obviously, the wall friction velocity is going to increase, but I'm going to assume that that is sufficient to describe the effect of roughness on the outer layer. In other words, the difference between rough and smooth here, the only quantity that changes is actually U tall. Whereas in the inner description, I've got this whole array of variables which I've now, for obvious reasons, I've jettisoned this, and I'm simply assuming that K is plus U tau are the two quantities that would describe the effect of the roughness on the inner velocity profile description. That's the first key point. And the second key point is something which highlights a good reason for looking at flows in internal geometries. The pressure gradient is fixed, so the beta becomes a constant, so therefore it can come out as one of the independent variables. It's a constant. So this problem then becomes y upon h comma u2 over UCL. And then I suppose that if I'm talking now about asymptotic behaviour, again, one might well suppose that the mean velocity becomes independent of Reynolds number at sufficiently high Reynolds number, then this is a measure of Reynolds number, and so U2 over UCL drops out, and I simply have F0 as a function of y upon h. flow is fully developed, then U2 over UCL, that's the skin friction coefficient, that's also invariant with X because it's fully developed. So this would come out anyway, either for a fully developed flow or in the case of the flow being high Reynolds number. So therefore, I can describe on inner variables, I can describe the effect of the roughness as y plus k plus, and the velocity deficit I can describe as a function y1h or y1 delta. So here's our friend. This is our cornerstone. This has got all the usual terminology that Philip went over yesterday. All I'm simply going to say is that if, and this actually appears slightly later on in another slide, if the log law holds up, in other words, we've got a sufficient scale separation, then kappa we can take to be universal, and B here is the additive constant, which one can take to be absolute constant. And if you think about it, if I extrapolate the log law down to an infinitesimally small value of y plus, then it's clear that the additive constant is actually a measure of what's happening at the surface, and that's actually important for looking at how we assess roughness effects. We'll go on to that a bit later on.
Well, I think on the type of previous slide, for the outer layer of the function g, I guess it should be g(O), not g plus. Right?
Oh yeah, you're absolutely right. Yeah, thank you. That wasn't deliberate. Yeah, so that's G inner, that's G outer.
Since the outer layer overlap with the inner layer in the slide, so that it has a log layer as it.
Oh yeah, okay. Yeah, okay. Yeah, yeah. That's a good point. Yeah, I think I'd sort of assumed that if there was a log law, then it implied that. Yeah, maybe. Yeah. Thanks. One important point for future use is that here's the log law. What isn't on that slide is the weight function. And I've written up Coles's weight function there. And the formulation is actually a straight separation of variables. Remember, in general, we're operating in 2 dimensions. And this is an empirical function, so pi is a function of x, omega eta. Eta is y over delta. And empirically, Coles suggested that omega of eta could be written as a cos function, cos pi eta. So that when eta equals 1, omega of 1 is 2. And so this Coles weight function at the edge of the boundary layer simply becomes 2 pi over kappa. I'll point it out, I'm sure it's pretty clear that pi, uppercase here, has nothing to do with 3.14, but that is indeed 3.14. So you just need to remember this. And what I'm going to suggest to you is that the log law is self-similar. And in these 3 really quite detailed steps, I'm going to suggest to you that at a large enough Reynolds number, or indeed when there is sufficient separation of scales, then we can also get a log law on a rough surface.
I have a good question. How do you get the value of 2 because cosine theta
Oh, so, if the log law is self-similar, then what we can suppose is that the only velocity scale is u4, and the only length scale is y. And that's simply a straight result from simultaneous overlap. In other words, if there is simultaneous overlap, the near wall length scale, which could be either nu over nu tall or the roughness height, that becomes irrelevant, as well as the outer length scale, and that could be delta, or it could be h, or it could be height radius. Those scales don't matter. So the only scale that matters is y. And that is what I mean by self-similarity or complete similarity. That means that the argument in the log function, I can choose that. I could write this as nu over u tall. I could write it as h, as long as it's describing the velocity deficit, or I could write it as k. That's complete generality. But it relies on there being a sufficient separation of scales. And what we can see is that if the Reynolds number is high enough, then those constants, these expressions here, which would normally be a function of k, they can actually asymptote the constant, which I'll come to. So the log law on a rough surface, it needs some minor justification and slight changes to what we would get on a smooth surface. The first one is, where do we have an origin? Well, these vary, but here I'm going to take it to be the bottom of the roughness, simply because I'm going to choose it to be somewhere, and that seems like a good place to be. And I need some sort of roughness, but basically the geometric origin is not the same as the origin that the mean velocity sees. And so there is an offset, or zero plane displacement, which represents the height at which the momentum flux is extracted, the mean momentum flux. So there'll be a slight offset. D is actually really quite small. Typically, it'll be a small fraction of K, the maximum roughness height. But the main effect is an offset on the log law. U-Tor, remember, that will go up, so there has to be an offset in relation to the smooth log law equivalent. And that really brings us nicely on to what exactly do we mean by transitional rough. Here I'm going to suggest that if K plus is less than about 5, we can expect the wall to be hydraulically smooth. That's not the only definition. I think Morkonen has a definition that REK, for hydraulically smooth, is less than about 25. So the Reynolds number on the roughness height is UK, the mean velocity plus past the roughness height, times K. And if there's a sufficient separation of scales, let's see what happens to this additive constant. What I'm going to do is to absorb y plus dependence, or take it into the additive constant by normalizing the log argument by k, not by nu over nu tau. And remember that if K is going to be very large, then nu over u tau ceases to matter. And K then becomes our inner variable in preference to nu over u tau. And the additive constant asymptotes to a constant, and that helps us to define these regimes. And I've actually taken these from Schlichting, and what he suggests is that when K plus is bigger than about 70, then V2 asymptotes to a constant. That's sort of the accepted definition of being fully rough. What happens between full roughness and hydraulic smoothness is when V2 actually increases before decreasing, and that's the transitional rough regime. When you look in the literature, it was actually Nicorazzi who first defined these regimes, and I'll come on to his roughness a bit later on. And that's why, if you look in some textbooks, this will actually be K plus sub S, and the S is for sand grain roughness, which I'll say much more about in a minute. So there's our log law, and here's the roughness offset. And Francis Harmer was the first guy who came up with this. So that's a primary measure of the effect of the roughness on boundary layer, provided it's fully rough, and also provided that you actually have a logger in the first place. And the enormous number is actually high. And there are actually other issues to do with this, about what happens to Coltz's weight function a bit later on, but other roughness definitions, what we could do is actually take the additive constant that we've just seen in the log law profile and absorb it into the logarithmic argument. So D is the offset that we just had, but now we actually have the roughness length, y naught. I know Beverly used Z because that's what meteorologists use, and actually also Alan Townsend uses Z, but here I've gone for Y. And using that for fully rough flows, this enables us to make an estimate of what the velocity shift should be by equating the log law, the smooth surface, and that. So here I've got the bits from the smooth surface, and then I subtract the difference from that due to the roughness, and this allows me to make an estimate of delta over time. And this is just to point out that we need to be aware of that difference. We're sort of getting towards lunch.
Good break now, it would be because then we're lines, and then we could start maybe 10 minutes early.
That would be good. I'm slightly behind.
Yeah. So what was the time that we should start? According to the schedule.
The schedule says start 13:30, so maybe we can start.
The challenges are presented by transition of roughness. So remember that by transition of roughness, I mean anything that is between the roughness height, which is somewhere between hydraulic and smooth and fully rough. And that leads really then into some recent work that we've been doing in a channel flow, where the roughness height is actually really quite large, typically 4–8% of the channel height, and some interesting results seem to be coming out. that are higher enough Reynolds numbers that on a rough surface we can actually have a log law. And what we can also do is to integrate that log law from the wall out to the centre line of the channel pipe. And ignoring viscous terms, we can in principle then deduce that the friction factor goes as 1 upon a square root of lambda 2 log RE root of lambda to the 0.8. And obviously this is implicit in lambda, and that comes straight from the log law, where if you remember U-Tor is implicit as well. So that's what this is. And I could equally write this as a Kalman number, R U-Tor on the cell. And this is really our starting point. Not that long ago, Beverley and co-authors, using the Princeton superpipe, extended the range of this friction factor relationship, really in the upper end of the Brown's regime, so the constants are slightly different, but to all intents and purposes, that doesn't really affect what we're looking at. And I can absorb this additive constant into the logarithmic argument like so, and that's the bit of the Frankel relationship we'll be looking at. And in walks Nicorazzi, 1932-1933. He actually did a really important experiment, and he actually indicated that for fully rough pipe flow, then the friction factor is related to the ratio of pipe diameter to something called Ks. Now I've introduced S as a subscript for sand grain roughness, and I'll say much more about that in a minute. And you can see actually the formulation is not that different, so there's obviously some appeal to the formulation that he came up with. And he actually showed that this actually works really quite well, and it's this function that form the basis of the tree chart. Nicorazzi actually did really the first systematic review of the effects of surface roughness, and unfortunately he used really a form of roughness which is really quite unusual. And what he did was to use roughnesses of a very narrow range of roughness heights. We could call this a monodisperse form of roughness. In other words, what he did was to get a sieve out, or a range of sieves out, different sizes, or bucket of low sand in each one and sieve it. And so ultimately, after several sievings, you end up with a range of roughness heights which are very closely related in terms of scale. So the distribution would be really a very narrow peak, and we did a range of these experiments with different values. And what that meant, of course, was that because the roughness elements were of the same size, they were also close packed. In other words, the effects where I was talking this morning about shielding, those are in there. And unfortunately, what we will see is actually that commercial types of roughnesses, rough pipes, rough anything really, the distribution is actually much more narrow, so you get a broad range of roughness types. And so from that point of view, the Nicorazzi experiments were slightly unusual, but it just so happened that in the mid-30s, that was really the basis of the systematic evidence that we have on the effects of roughness. So, about 10 years ago, Peter Bradshaw came out with this rather wonderful phrase that you could actually treat Nicorazzi's experiments, or this quantity, which is called the sand grain roughness height, as rather like a dollar bill, or let's say a €10 note, or even a krona note, what denominations they come in. But the point is that what he's suggesting is that the actual note itself, i.e. the Nicorazzi sand grain roughness height, is valueless in itself, but it's a common currency. In other words, what you could actually do is to take his law, and for a distributed roughness, you know what the friction factor is because you've measured it, and from that you can estimate what the equivalent sand grain roughness is. So that's the currency of usage, simply because that is the core of the experimental evidence that we have. But also, if you don't use KS, what do you use?
Right, so a bit more about that later
And
on.
this is a chart from Nicorazzi's paper. There's one on smooth pipes and one on rough pipes. And if the flow is laminar, then you get a parabolic velocity profile, you can integrate it, and laminar turns out to be inversely proportional to the Reynolds number. And the Reynolds number here is based on the volume average velocity times the time interval. So that's equation 1. Equation 2, something I've not mentioned before, is the Blasius empirical formulation for the friction factor. And this is line 2, and it's based on smooth data. And then 3 is Prandtl's friction factor law. And then here, in blue, I've plotted the effects of varying the relative roughness. So on Nicorazzi's data, he actually used the inverse of this. But basically, as Ks increases, then obviously the friction factor goes up. But in so doing, it becomes independent of Reynolds number, and that's what we mean by fully developed roughness or fully rough flow. And the most interesting feature of this, of course, is that here's the smooth line, here are the rough lines, and in between you can see how the distribution of friction factor is inflectional. And that's really the key area, because it's the area of what we call transitional roughness. And what is so difficult about this is that Nicorazzi's data at the time were the only data that actually showed this inflectional behaviour. And that in a minute you'll see how there are other types of commercial roughness which did not show this inflectional behaviour. And you could argue, well, that's because he used this rather curious form of roughness. In other words, his close parent, sand grain roughness, one is verse. And this actually led us to, leads us to the Moody chart. So you can actually see it's got much of the information that we saw in the previous plot. Here's the laminar regime, here's the smooth line, here's the effects of relative roughness. But there's a difference, and this is our friend Major Colebrook. What we have here is an inflectional response in the transitional regime. Go to the Moody chart, and that inflectional behaviour has actually disappeared. So the question is, how did that happen? Well, Colebrook came up with his transitional roughness function. So here's Nicorazzi's logarithmic argument. Here's Prandtl's logarithmic argument. And he simply sort of averaged them out in some sort of curious way. It's actually what you formally would call the harmonic mean, which is, let's get this right. So if I want to work out what this function is doing, I've got to pay attention to the logarithms. But basically, if I take 1 upon A, take 1 upon B, that actually gives me the reciprocal of the average. And if one were being slightly cynical, well, you could have thought, well, actually, why not take the geometric mean? Okay, why not take the square root of their product or something like that? So it was all really rather curious. However, it actually gives you nice smooth lines. Well, I suppose one good thing is that small relative roughness, then this argument, or this part of the argument, disappears. So you should get back to Prandtl's law. But basically, there's no real theoretical justification for taking this formulation argument. And what he also did is that you can rejig this to make the appearance of the sand grain roughness really rather more explicit. So here, on the left-hand side, you can take this function and plotted as a function of sand grain roughness here. And you can deduce this formulation from that. And so it just sort of makes the dependence of the variables slightly clearer. And he based that on the idea of his set of experiments in a rough channel. This is the smooth channel. This is his Nicorazzi equivalent, smooth sand grain roughness. And then what he did over the next two sets of roughnesses was to actually introduce these large roughness elements, and this is really his key contribution. And the roughness grains, these large grains, are about 10 times the size of the sand grain roughness, but they only occupy about 2 or 5% of the surface area. And I'll say a bit more about these other two forms of roughness. So here's the detail. Sand grain roughness, it's a type. Friction factor, equivalent to sand grain roughness, that's defined here. And 2, you increase the large grains by, you put them on 2.5% of the area, and then on 5% of the area. And then the next variation is where you keep this density of large grains the same, but then you actually play around with the ratios of sand grain, small sand grain roughness, and the smooth surface. And these were his results, which are really quite intriguing. So here we've got friction factor against Reynolds number, 1. Here's the Nicorazzi dip. You can see how it's actually part inflectional, but then it actually disappears. The reason for that is that the large grains come into effect, and they're exerting a disproportionately large effect, and obviously the friction factor goes up. But then I take Colebrook 3 roughness, it's replotted here, and then I start playing around with the background sand grain roughness, the small stuff, and I reduce that so that I increase the area of the smooth surface. And what happens there? Well, turns out that departures from a single variation only become apparent at really quite high Reynolds numbers. And that's an effect, again, of the small influence, or small sand grains becoming really quite inconsequential, and that's because of the shielding effect, this blockage of the small grains by the large grains. And this is the key plot. This is Colebrook's function. And on here, we've got Prandtl's smooth law. This tells us that the right-hand side of this function here should asymptote to a constant on these axes once we get to the fully rough condition. And what he's done is to put on his 5 roughness types, and he's also included some commercial roughness here, really just to show how this behaviour is actually really quite gradual. And then what he did was to fit his function to his own data. Well, honestly, I think if one of my students said, these data fit these points, this function, I'd say, well, go back and do it again. And so this is actually the form of the function that actually appears in the movie chart. And it's supposed to be based on his own data. So there's a question mark there. Another slightly difficulty with Colebrook's function is that this should asymptote to the smooth line at small relative roughness. But you can now see, actually, that it doesn't really, but the Colebrook function is actually always slightly above Prandtl variation. So one of those problems is simply the result of really not really very good clear thinking about fitting a function to data. The other one is simply the behaviour of the function as it's formulated. Well, let's get back to basics then. Here's Prandtl's smooth law. These are the Colebrook data. And interestingly, you can see again this inflection of behaviour that comes from Nicorazzi's data. That's apparent in this first case. And then actually, as you increase the proportion of the large grains, then you can see how this inflection of behaviour disappears. And that was really the justification for his function. But if I look at, in particular, let's say Colebrook 5, then you can actually see that there's no real inflection of behaviour. And this is actually a reworking of Claus's data. What he did was to take Colebrook's data and then plot them using the Palmer roughness function. And the roughness function is defined as this. And if you're not sure about that, then I can formulate the log law like so, with the roughness offset delta UR there. And just by playing around with the arguments of the log functions, then it turns out that delta UR is simply the difference in the two active constants plus this expression of 1 upon kappa log k plus. And so very faintly, sorry about this, these are blue diamonds to my eyes, but there's a very faint blue line here, and that is the Colebrook function as defined by this quantity, which actually comes from Hummer. But it's a straight plug and play from this to this. So this is the Colebrook function on these axes. These are the Nicorazzi data. So again, you can see that there's inflection of behaviour, and there is on some of Colebrook's data, but you can see that there's actually still a difference between the Colebrook function and his own data. All I'm here, the reason why I plotted this is that I'm making the play that if you really want to examine roughness effects, then you should do so by looking at the Hummer offset function. In other words, you should look at the vertical offset caused by the effect of roughness. And this is really where we are. There's not much to be said about the Colebrook function, other than when reading Lewis Levy's paper, famous paper, it was rather fun to see how Major Colebrook had actually gone on to, well, possibly better things. So he wrote his papers at 33 and 47, and then left on a fast boat to India. In Princeton, they carried on looking at roughness effects, and this pretty much echoes what I've just been saying. The only difference is that now we're actually relying on much better data. We're not supposing that we're inserting additional roughness elements to find out how the roughness function changes. All we're simply doing is taking a pretty rough pipe and honing it, and when you hone it, it introduces a spiral wavelength on the roughness. But despite that, the roughness actually turns out to be pretty well Gaussian. It's not that far from Gaussian. And when you do that, again, you can assess the Colebrook function in two ways, as we've just seen. You can either plot the friction factor against Reynolds number. In so doing, here's Beverley's smooth line, so that should be close to the Prankel line. And here are the rough pipe data. Here are Nicorazzi's data, and this is the Colebrook function. What's interesting about this is that this is commercial roughness and actually shows a bit of that inflection of behaviour that appeared in Nicorazzi's data. And if you plot the Hummer roughness function, again, as we've just seen, for the rough pipe, these results against Colebrook's function, you can actually see there's really quite a considerable difference. And so what I'm really saying is is that that Colebrook function was the basis for these nice smooth curves on the movie chart. But there's really quite considerable error between the two. I think it's something like, the worst case, it's something like 20% on friction factor. So, this is really a summary of what I've just said. I've covered that in the interests of time, and I'm going to press on. In the literature, you will come across both K-type and D-type roughness. D-type roughness work still carries on. I would suggest that it's really quite a curious form of roughness, quite simply because if you have these span-wise ribs like this, then you get, or can get, trapped vortices. And obviously it depends upon the wavelength of the roughness, whether these vortices are trapped, in other words, whether you actually have a cavity which is open or closed. And what in Townsend's book, which I would encourage you to have a look at, he actually discusses this D-type roughness and suggests that actually what you get with this form of roughness is a sort of a captured vorticity which then erupts into the outer regions of the boundary layer. So I'm not going to say too much about D-type roughness, but really that actually serves as quite a nice trailer for the roughness that I do really want to have a look at. It's this, what I've called this 2.5D mesh roughness. One time I had a very obliging undergraduate student, and I said, well, Mandelbrot has told us how to, this is the typo that I did actually manage to find. I think in your notes this is an N, that's obviously wrong. She spent some hours mastering a team where they actually built these fractal roughnesses, so you can see that the formation of the roughness is fractal, or certainly is self-similar. So here are 4 big ones, and then dispersed around the 4 big ones there are 4 lesser ones, and around each of the lesser ones there are 4 even smaller ones. And from this you can actually define a fractal dimension, and we did this for a range of surfaces. We did hemispheres, cubes, and these tetrahedra. And the fractal dimension of these geometries is about 2.5. But it soon turned out that really this wasn't really a well-designed experiment, simply because, as I mentioned previously, if you've got a large element here, then there'll be some sort of Reynolds number at which you start to get shedding of this roughness element. Or you could actually get some sort of standing vortex pair. And once that happens, then obviously things like form drag, or the ratio of form drag to friction drag around individual elements changes drastically. And your fractal dimension isn't actually going to tell you very much about that behaviour. You need some sort of Reynolds number information, or some sort of information fluid responses. So that's what you don't have. So this was actually a fairly pointless experiment. It's actually very interesting and fun for some of us. Another way of defining these surfaces is simply, because it was all self-similar, you could actually work out the area, surface area of these roughnesses, or even the volumes, and then work out a length scale based on the square root of the area of the volume. And that was actually quite interesting, but other than that, it didn't seem very much. Okay?
Can I have a question on that one? When, I mean, the formula will be quite three-dimensional in the sunlight, or when would you expect it to become two-dimensional? At what time? Because at some height you will not see the surface flashes anymore. Do you have an idea about that?
Something like 10 large roughness lines. I'll come on to that, because that was actually a fundamental decision that we had to make at So very quickly, these are our fundamental definitions. Key question, Townsend outer layer similarity. Is that sufficient to describe the effect of roughness? In other words, are the effects of roughness confined to the roughness subgroup? That's the dimensional analysis. That's the typo, and this is really what we're going to focus on in a minute, as well as the similarity. That's Harmer's roughness function, other definitions of the roughness function, and also this is just a reminder of how we're actually going to use the log law in the next experiment. In other words, you're going to use this meteorological definition. And this actually follows on from Henrik's question. But, what we're actually going to do is to assume a value of kappa. I'm not going to kappa everything in this particular, it's far too difficult. So we're actually going to take a value of kappa and move on to 1. And in so doing, if we get the value of the surface friction from the pressure drop down the channel, then it actually leaves the roughness offset and the roughness length scale y0 as 3 parameters, which we do by 2 parameter fit. So those are the 2 quantities that we actually get out of assuming as a log. This is what we want to do. This is all really about testing the boundaries or the limitations of the basic ideas on self-similarity and Townsend similarity that we've been looking at. In other words, let's give the fluid a really good kick by using large roughness. And how well does self-similarity of the mean velocity profile, and how well does outer layer similarity, how well is that there up? So it's really testing the limits of these ideas. And our starting point was to look at Jimenez's review, and he suggested that if you keep K upon H less than 2.5%, then similarity rules can be expected. And, okay, well then let's make K upon H at least 4%, and in so doing, if we do that, are the details of the roughness, do they reach the outer layer? What happens to self-similarity? And as a reminder here, remember this morning I said that self-similarity as deduced by simultaneous overlap is a stronger condition than Townsend outer layer similarity. That's because this requires independence of 2 imposed length scales. And this requires nearly the motion collapses on a single length scale. So I would argue that this is a stronger constraint than that one. This is how we did it. Pretty standard channel. It's actually very similar to an experiment done by Bakken and Krogstad. I think one chose for somebody who's now working over Krogstad, so he probably knows all about this. So our experiment is actually very similar to theirs, except the roughness elements are different. And traverses were done at H is the half channel height, and X upon H is 132. And roughly at about 120 H's, we get fully developed flow. And so that actually gives us a couple of meters over, we can actually measure the pressure drop, so we can actually get the skin friction quite accurately. And I think U-Tor, I think, has an accuracy of something like 3% on it, so that's sort of respectable. When we did the smooth channel equivalent, of course, then things are really quite different in that you need a much longer channel. In our case, we actually needed a new laboratory in order to get a sufficiently long channel. So there are things that we had to deal with there, but they don't actually affect what I'm going to say. So here's the roughness that we looked at earlier on. Here's the isotropic grit roughness. remember that it's got a skewed distribution. It's not isotropic, it's not Gaussian, but is isotropic. This is our pathological roughness. These are percentages, so because these are distributions, going from here to here, that tells me what the maximum roughness height is. So this is 4%. This is actually, I just realised it's actually in millimetres. This actually should meet 80%, but the details are on the next slide. But the important thing is that there's a huge peak in the distribution here, zero roughness, and that's because of these huge areas in which the surface is smooth. And then you get another little peak here where you get these roughness elements. But the maximum roughness height goes from here to here, so it's actually 4 millimetres or 8% of the jump height. And then here is our smooth wall roughness. So again, as we looked at this morning, for good reasons, we're taking the governing roughness length scale to be the maximum, so it's the width of those distributions. So it's 4% in the case of the grit and 8% in the case of the mesh. And these are the details of the mesh. That's okay. Well, near wall measurements on a rough surface are bound to be difficult. L plus is between 40 and 60. Sure, Rams has got a view on that, but turns out actually we'll be looking mostly at either the medial or outer layer similarity, so I'd argue that resolutions are too much of a problem. That is simply a problem with using a hot wire that's somewhere between half a millimetre long and 1 millimetre. And obviously because the wall friction is so high. So we looked at 3 Reynolds numbers on the grit surface, 3 on the mesh surface, reference smooth surface, and again, just as a reminder, K plus here is based on the maximum roughness height. You can see it's actually huge, several hundred. Generally in the literature, people go up to about 100. So obviously, what we can do is actually push it back. Another typo, the additive constant in the log law. The origins of this typo are really quite complicated. I only found out this morning that on this plot, anyway, the additive constant should be 5.4, which is actually a lot more respectable than 4.3. But it's actually to do with correcting for the effects of not having quite fully developed flow of the smooth wall case. So this is the smooth wall boundary layer. This is the log law. 1 upon kappa, 0.41 log y plus the additive constant of 5.4. And what we've included here, because it's actually a very similar experimental data from Colin Martin Backen's PhD thesis. And you can see that as you increase the Reynolds number or roughness height, then the wall friction creates an offset the Harman roughness function. So we move the moment so that we move both down and to the right. And then we use Backen's data here as a point of reference. Here you can see the grit roughness, and here you can see the mesh roughness. And now we actually come to looking at the mean velocity profiles and the deduction of whether flow is self-similar or not to if we've got a log law or not. And we're going to do it using this meteorological definition of the log law. And again, it's a 2-parameter fit, so that we can estimate D and we can estimate Y naught. And we can build those corrections into the plotting of these data. And when we do that, you can see that we get a regional collapse for both data sets. And they occur between values y-0 and y0 of 15 and 30. Now remember that in terms of asymptotic matching, y, or rather y0 is our inner length scale, or imposed length scale. In this case, the other one, the outer scale, will be h, half-channel height. And so what we require for simultaneous collapse is that these profiles, when plotted on outer scales, should also show collapse. So that's what we're looking for. Okay? And these data suggest that we should be looking through values of y and y0 between 15 and 30. So we come to the outer and for good measure, what we've done is to put on the smooth data. These black chain lines here are the log law on outer scales, but what we've done, we've kept kappa as 0.41, obviously. That's the value of kappa that's used to estimate the offset D and the roughness length scale y0. But the additive constant is just free simply because we're dealing with both smooth and rough surfaces. And it's a bit cluttered, but don't worry, we'll deal with that. And let's look at the grit first. So the grit lines are sort of chained and dotted, and you only need look up here, and there's a better plot coming in a minute, where they do actually collapse in this region here, and they collapse on a line which is on a slope of 1. And it has to do so over the corresponding range of inner scales. So I would suggest to you that grit surface collapses on both inner and outer scales for this range. I'm going to give a caveat now, and that is that data are always in the eye of the beholder. And when you do this sort of experimental work, some people think the data collapse and other people don't. So you make your own deductions. But I would suggest to you that these data collapse on both inner and outer scales. What about the mesh? This is the corresponding range of y upon h for this range of inner scales. And I know it's cluttered, but we're coming to that, don't worry. These are the mesh data, and they're beginning to break away from contract slope. And so here's the detail. These are the same data, but we've stripped it down so that these are the mesh data, and I'm going to suggest to you that they only collapse once you get to a y upon h bigger than about 0.3. And remember that for simultaneous collapse, we actually, because of the inner scale, we have to actually look down here. In other words, this goes from about 0.1, 1.12 up to about 0.25, when what I'm actually saying is, well, according to the detail, then we don't actually get collapse until y on h of about 0.43 again. Now, Henrik's question was, well, okay, you've got periodic roughness in span one's direction, so how do profiles vary when you go from a crest of the roughness, so that's on top of the roughness, to the valley or the trough here. And so what we did was to look at these three profiles. So I've got trough, crest and mean. And these are obviously time averages, but in the case of the trough and the crest, they are only averaged at these span-wise locations. And what I'm suggesting to you is that for a log law to exist, we need simultaneous collapse between here and here. And what I'm suggesting is, well, that's not quite true. It's a sort of a tangential collapse. But in any case, anyway, what the profiles tell us is actually that we don't actually get out of collapse until we're really significantly outside this region of where we're looking for simultaneous collapse. So that's the first moment. What it seems to suggest is that we've got a log law on the grit surface, but not on the mesh surface. Here's the U component stress, and look how well they collapse. Actually, amazing. Townsend similarity actually shows up remarkably well. So those are the same data now, but they are plotted with other data. So the symbols are actually Backen's data, which are all these symbols here. And then the gold colours are, it's a sort of a, if you like, a global visual average of the data that comes from Jimenez's review. And that actually includes both data on Bangeres and on channel flows. There is one idiosyncrasy about these data, and that is that you can see that there's a bifurcation here, and that some data, including ours, actually roll off down towards the wall. And our, I can't quite see it, but our data have an RE tour in the region of 5,000, and they coincide with Backen's data for an RE tour of less than 1,200 only. When you go up to RE tour above 1,200, then you seem to get this slightly different response. I'm not quite sure why. If you go to skewness and flatness, skewness is actually quite tricky to collapse, and that's quite simply because it's an odd order moment, and so you're averaging about 0. So it's always slightly tricky. But, one could argue that Townsend similarity works for a y on h bigger than that 0.6. And then the fourth order moment behaves rather like the second order moment, in other words, you get good collapse for a y on h bigger than about 0.3. So, I'm getting there. I've got about 10 slides. So, carry on. So, what do we learn from this? One thing that I haven't discussed yet is the wake strength. Let's come to that in a minute. The first thing is that, as I've said, we think that we can demonstrate self-similarity on the grit surface, but not on the meshed surface. So that's an interesting result. Because the mesh roughness is periodic, there's the question which I forgot to mention, which was in response to Henrik's question, which was at what point does the mean velocity become span-wise homogeneous? In other words, it becomes independent of the mesh. It loses the periodicity that the mesh has. And that occurs at a distance which is that's not quite right. That can't be right. I'll have to go back and check this. No, that's far too big. I'm sorry about that. I'll have to check that. It might be 0.08, but let me check that. But we really only get collapse for a Y1H bigger than 0.3 is outside the region of the expected value. Now the wake parameter, Coles' wake strength that I defined this morning. You can go to the mean velocity profile plots and you can estimate what that should be. For the smooth, 2 pi upon kappa has a value of 3.2, and for the grit it's 0.82, and for the mesh it's 0.61. In other words, the wake strength has decreased. And that's a curious result, because what it suggests is that the effects of the roughness are actually reaching the wake region. But the thing about the wake region, of course, is that the way Coles formulated it actually only means something if you have a log law, so that if I we've got the theory of log law, I can only define this this wake strength if I'm actually sure about there being a log law. In other words, in the case of the mesh roughness, to define a wake strength isn't actually terribly sensible. So this could either be a genuine reduction in the wake strength, or it could be a meaningless statement because we haven't got a log. I suppose the other point is that the Townsend outer similarity is actually really quite robust, and that's true for both channel flows and also boundary layers. And I suppose when you think about it, then we've got fully developed channel flow, so the pressure